All right, so in this video, we're going to talk about the alternating series estimation theorem. So what this theorem tells us is that if you have an alternating series that is convergent, so we have to make sure there's an alternating series, there is a convergent series. So this is true, where U1 are the list of the terms in our sequence, they're positive. And this sum is alternating, so it satisfies the alternating series test. So these are the conditions. So once you know it is a convergent alternating series, then we can say the following, that the remainder terms are n, which is really the s, the limit of that sum, minus the nth partial sum. That's going to be always less than or equal to u sub n plus 1 term. So this is a lot of things that we're saying here, but I do want to break it down a little bit more for you so that you understand this inequality. So this guy right here, this is your sum. So that's the actual value of the series. And this right here is the nth partial sum. So this is your nth partial sum, Sn, when you're summing off nth term of that series. So we're saying that when you do that subtraction, your actual value and take away the partial sum, you're going to have a little bit of error left. And that's what this is. So this is what we're calling the error. And the error is going to be always less than or equal to the next term, u sub n plus 1 term. So that's what really we're saying. So let me give you another illustration so that you understand this inequality a little better. So here's an illustration for this. So suppose you have your alternating series that converges. So we have some alternating series, negative 1 to the power n, let's say a sub n or u sub n, whatever you prefer. So this is going to be, let's say, a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus all the way up to a sub n. So I'm going to make this a negative term, and then plus a sub n plus 1, which is the next term after a sub n, minus a sub n plus 2 plus Keep going, infinite number of terms. So if you add up these guys right here, this is your Sn, which is the nth partial sum. And but we know that this converges, so all of these infinite number of terms converges to some s. So that means whatever terms we leave out, so from a sub n plus 1 all the way to that, that's how much we leave out. Those are the errors. So this is our r sub n terms, the remainder terms. And this can be computed by taking the whole, which is s minus Sn. And we throw an absolute value just to make sure they're positive. So that's what we're really saying here, that our error is going to be less than or equal to that u sub n plus 1 term, or really a sub n plus 1 term. That's what we're saying here. So let's go ahead and take a look at some examples so you know how to use this inequality. So for this alternating series, we want to determine how many terms should be used to estimate the sum of the entire series with an error less than 0.001. So this is a convergent alternating series. So you can verify that, but I verify that for you. This is a convergent alternating series. So, well, we want to know the following. So we want the following. We want the error to be less than or equal to 0.001. So we want this to be less than a sub n plus 1 term, but I want that to be less than 0.001 because we want the error to be less than that. We know r sub n, which is the error, that's always less than a sub n plus 1 term, or u sub n plus 1 term, whatever notation you prefer. So what is our a sub n plus 1 term? Well, this is the a sub n term. So this is your a sub n, which is 1 over n squared plus 3. And which means that your a sub n plus 1 term would be 1 over n plus 1 squared plus 3. So let's plug that in here. So this is 1 over n plus 1 squared plus 3. And we want that to be less than 0.001 or 1 over 1,000. That's another way to write 0.001. All right, now let's do some algebra and solve for n, because n will tell you the number of terms you need to add up, so the error is less than 0.001. So I can cross multiply. This is 1,000 is less than n plus 1 squared plus 3. And then we can switch the inequality, switch the terms. So we can say that n plus 1 squared plus 3 has to be greater than 1,000. Algebraically solving this, so I subtract 3 from both sides. So we have n plus 1 squared is greater than 997 when you subtract 3 from 1,000. Then square root both sides, so you're going to get n plus 1 is greater than a square root of 997. And then I subtract 1 from both sides, so we must have n greater than a square root of 997 minus 1. Now, if you put this in your calculator, you're going to get about, I believe, 30.5, something like that, but n has to be an integer, so we're going to round it up. So we're going to say n has to be greater than 31 or 32 or 33. Let's say greater than 31 is good enough. So as long as you're greater than 31, if you have greater than 31 terms, then this sum will have an error less than 0.001. That's what this means. Okay, so here's another problem. Again, we want to do the same thing. We want to find how many terms we need to use so that the entire sum is estimated with an error less than 0.001. So we want the error to be less than our a sub n plus 1 term, and that has to be less than the error 0.001. So let's figure out our a sub n plus 1 term. So we know this is our a sub n term. So our a sub n plus 1 term would be plugging in n plus 1 everywhere there is n in the formula. So it'll be n plus 1 plus 3 times a square root of n plus 1 cubed. That will be the formula for this. So substitute that for a sub n plus 1. We will have 1 over n plus 1 plus 3 times a square root of n plus 1 cubed. We want that to be less than 0.001, which is 1 over 1,000. And then again, doing the same thing we did earlier, cross multiply. So you have 1,000 that's less than n plus 1 plus 3 times square root of n plus 1 cubed. And then we switch our direction of the inequality. So you have n plus 1 plus 3 times square root of n plus 1 cubed that's greater than 1,000. And now we're going to go ahead and take cube root on both sides. So you'll have n plus 1 plus 3 times square root of n plus 1 greater than the cube root of 1,000. And we know cube root of 1,000, that's going to be 10. All right, so we want the expression on the left-hand side to be greater than 10. So we have, I can subtract 1 from both sides, so I can get rid of this. So that will give me n plus 3, a square root of n plus 1, greater than, take away 1, that's going to be 9. Now, solving this algebraically is a bit difficult because you have n in 2 different places. So we're going to start guessing some values for n. So I'm going to choose n to be 1. So if n is 1, we have 1 plus 3, a square root of 1 plus 1. That's 1 plus 3, a square root of 2. So that is not greater than 9. So that's not true. Now let's pick n equals 2. So we have 2 plus 3, a square root of 2 plus 1. That's going to be 2 plus 3, a square root of 3. Again, that's not greater than 9. So it doesn't work. It's still less than 9. So keep going, selecting values for n. So you can see that if you maybe, let's go for one more. Maybe we'll have a better idea. So if I do n equals 3, I have 3 plus 3 square root of 3 plus 1 So this is a nice number. So this is 3 plus 3 times square root of 3 plus 1, that's 4, square root of 4. So that is going to give us 3 plus 3 times 2. So that's 6 plus 9. So this is actually 9 equals 9. All right, so we don't want that. It's still not greater. So what I'm going to say here is that 9 is not greater than 9. So that's not going to work. So the next value for n will definitely work. So if n equals 4, you have 4 plus 3 times square root of 4 plus 1, which is 4 plus square 3 times a square root of 5. Now, if you put this in your calculator, you will get a value that's greater than 9. So this is checked. So as long as n, so n has to be greater than or equal to 4 for this sum to have a total, for the total sum to have an error less than 0.001. All right, so I hope this helped you understand the alternating series estimation theorem. Take care, everyone.